Hello everyone, welcome to another lecture of control systems. In today's class we are going to see how to compute the steady state error using your generalized error coefficients. So this is an alternative method to the partial fraction method of finding steady state error. So both are the same, they do find the steady state error. So the first method was using the partial fractions, which we have seen in the previous lectures, and in today's lecture I'm going to show you another technique, which is your generalized error coefficients. So I have seen some of the assignment 2 questions are based on this, so I thought I'll expose you to this method also. And in your exam normally there is no distinction, they just ask you to find the steady state error. And I've never seen a question where they specify the method by which you need to compute the steady state error. So hopefully it will be the same for this time also, but nevertheless we will see this method, and you can use whichever method you find it easy for solving and computing the steady state error. Good. So the generalized error coefficient method is in the form of a series expansion, and it has coefficients C and R, where your C is computed by or computed from the Laplace transform, or it is computed from your transfer function or the f of s. So it is computed not from the transfer function. I would say it is computed from the error function more or less. And then your R of t is something that is computed from your input signal. So we'll see how what are these and how do you compute this given a system, a feedback, and your input signal, right? So we will be given, so for any system we have a system function g of s, then we have a feedback function h of s, and then you have your input signal or the input function r of s. So these are the three parameters that don't change in any question, and from these three parameters you have to find the steady state error using this generalized error coefficient method. And how do we do that is we compute the C0, C1 and C2 to be a limit based method. For limit s tends to 0, d by ds f of s d square by d square. So as we go up the order of coefficients, the differential also, the order of differentiation also increases. Then your r of t, r dash of t, and r double dash of t and r triple dash of t are d by dt, d square by dt square, and d cube by dt square. Then what is left is our f of s. And what is your f of s? F of s is equal to 1 upon 1 plus g of s plus h of s. Alright, so now we have everything. So given any question, we will be able to solve this and find the steady state error using this formula, because now we know what each of these expressions stands. The derivations are not important, so you don't have to learn the derivations on how to compute C0 and R of t, but you need to remember the formulas and you apply these formulas on a given question, something similar to this. So a question is given for a given system. So your system function is given as g of s, and that is equal to 1 upon s plus 1. Okay, good. And your feedback is probably going to be an unity feedback, which means my h of s is equal to 1. So that is your unity feedback. And then what do I need is I need my input. So my input r of s is given. So that also has to be given in the question. So these three things will be given to you: g of s, h of s, and r of s. And from these three inputs you can find the C0, C1 and C2, then RT, R dash T and R double dash T. So let us say this method asks us to specifically use the generalized error coefficient method. So which means I'm going to be using this method. E of t is equal to C0 R of t plus C1 R dash t plus C2 by 2 factorial R double dash t plus so on. So what is my R of s? My R of s is equal to 1 by s plus 1 by s square. So that is also a part of the question. And now coming to my solution. So let us find, so what we can do it, we have to just calculate these coefficients. So first let's see how we get our R of t. So your R of t is obtained by taking the inverse Laplace of R of s. So L inverse of R of s, gives you your r of t, right? So that is 1 by s plus 1 by s square, and that is equal to, so the Laplace inverse of 1 by s is just 1, and my 1 by s square is t. The r of t is given to be 1 minus 2t. Good. So the Laplace transform of 1 by s square is just t, and 1 by s is 1. And then your f of s is given to be 1 divided by 1 plus g of s into h of s, and that is your s plus 1 divided by s plus 2. So I have computed my f of s and my r of t, and now I'm going to find with these two. Now I can do my r dash of t, which is minus 2. I can easily tell my what is my r dash of t, that's going to be minus 2, and your f of s is this, so we can find c0, c1 and c2. So r of t is 1 minus 2t, and the f of s is s plus 1 upon s plus 2. And now my r dash of t is minus 2. I can just write that here. Right. So now with these two I can compute pretty much all the other parameters. So let's start with my c0, that is limit s tends to 0 f of s, and that is something like this, s plus 1 upon s plus 2, and that is going to come to what, 1 by 2. Alright, because I just put s is equal to 0, and then 0 plus 1 upon 0 plus 2 is 1 by 2. Then my c1 is limit s tends to 0 d by ds of f of s, and that is equal to limit s tends to 0 d by ds of s plus 1 divided by s plus 2, and that is equivalent to what? So now I have to do the differentiation, and this is of the form u by v, and my differential formula is going to be v du minus u dv upon v square. Right, so I'll write the formula here, and then I'm going to apply the formula there on the right hand side, and then obtain the d by ds for my rational expression, and then let us see how the limit applies to it. Good. So let us do s plus 2 into d by ds of s plus 1 is d by ds of s plus 1. Let me write that here. Minus your s plus 1 into d by ds of s plus 2. So what you take u and v, you have to be very careful, because u is the numerator and v is the denominator. So you cannot change the order of the numerator and the denominator, because your the values will be entirely different if you do so. Yeah. Okay, so that is simplifies to this divided by s plus 2 the whole square, and then I apply my limits to it, and what do I get? I get 2 minus 1, 1 upon 0 plus 2 the whole square. So I should be getting somewhat, from my calculation I'm telling it should be 1 by 4. Let's do it in steps and see what do I get here. Good. So that is what I have on my right hand side is my d by ds of f of s, right? So this is my d by ds of s plus 1 upon s plus 2. Now let's apply the limits. So the limit of s tends to 0, when I apply that to 1 by s plus 2 the whole square, I'm going to get 1 by 2 square, right? And that is going to be equal to 1 upon 4. So my C1 is equal to 1 upon 4. See, this method is also easy, because here only thing you may have to brush up on is the differentiation, because every time you have to do d by ds, d square by ds. So when most of the second order systems and the first order systems in control system happens to be a fractional, happens to be in fractional form, because they are pole dominant. So you definitely have a denominator, significant polynomial in a denominator. So which means you're looking at an u by v derivation, right? Your differentiation is always going to be having the form u by v. So which means you need to be very careful when you do this differentiation of fractions. So that is the only thing you have to look out for in this method, and all the other things, we have our C1, we have our C0, we have your R of t, and you have your R dash of t. So there is a correction that the question is minus 2 by s square, because no, that is what that is what will give you as minus 2t. I don't know how I wrote. I got mixed up with 1 by x and 1 by s square. Derivation and Laplace transform. I got mixed up with the formulas for your Laplace transform and your differentiation. So you should not, end up with that confusion in your exams. So, and this is your steady state error. So for your exams, just write it till E of t. That should be fine. But if you want to find ESS, so the ESS is given by taking the t limits to infinity, right? So by putting the limit t equal to infinity, you get ESS, and that is also something you can do. And then in this case, I can easily tell that since my t is in denominator, it's in the numerator, my ESS is gonna be infinity, because anything you add to infinity or anything you subtract from infinity, the value is still gonna be infinity. So in this case, I'm going to get it as 1 minus infinity, so it's going to be a minus infinity. But if you do till E of t, that should be fine. You can do one more step and do the ESS calculation. Most of the time your ESS will come out to be infinity if the t is in the numerator. If the t is in the denominator, then you may get a 0, because 1 by infinity is 0. So that is where you get a non-infinite value for ESS. Okay, good. So now another numerical where my G of s is 1 by s plus 1, and my R of s is 1 by s square, and minus 3 by s cube. So we are going to use the same generalized error coefficient formula for this. And now I can find my R of t. So for my R of t, I need the inverse Laplace of R of s. And then here I am going to highlight the formula, because in the last numerical I just made it wrong with the formula for my inverse Laplace. So here I'll clear that formulas for you, and then we will do this numerical. Alright, so this is the formula that we are going to be used, the series expansion for my generalized error coefficients. And now what is the Laplace formula? So let me just write those for you. So your L inverse of 1 by s is equal to 1, and your L inverse of 1 by s square is t, and your L inverse of 1 by s cube is t square. So these are the formulas, t square upon 2 factorial. See, these are the formulas that you need to know, because in your exams they don't ask beyond s cube. So S cube is the maximum difficulty you get in your exams and in many of the questions. So if you know these three formulas, you must be pretty much, you will be able to apply the inverse to any of these formulas. And these are already in partial fraction. No, these are already in partial fraction terms. So we can directly apply the inverse. They are inverse compatible, right? That's what I'm trying to say. This 1 by s plus 1 by s square minus 3 by s cube, they are inverse compatible, meaning that you can directly apply the inverse, and you are going to get it as 1 plus t minus 3t square by 2. Alright, and then your r dash of t is 1 minus 3t. I'm just differentiating my r of t, and my r double dash of t is minus 3, and r triple dash will be 0. So I can go till r of t, r dash of t, and r double dash of t, which means I need to be finding the coefficients C0, C1 and C2, right? So because my R0, R dash and R double dash are valid, so I need to find my C0, C1 and C2, the corresponding coefficients from the limit s tends to 0 in the S plane. And now for that I need my f of s, and what is your f of s? Your g of s is given and h of s is equal to 1, and your f of s is given as s plus 1 upon s plus 2. Right, so this is the same we have what we have seen in the last question also. So that means I'm again going to get my steady state ESS to be infinity, but Yeah, so let us just calculate the other values, right? Everything up to that step should be still informative for us. So the d by ds of f of s gives you the c1, and this is again your fractional differentiation, that is u by v. So you have to do it in the same way as we did it for previous, u v du minus u dv divided by v square. I'll do the same, and I think this is the same, so I should again get it as 1 upon s plus 2 the whole square, right? So that will be my c1, and then that is and then, but now I have to find one more, because in the previous question we did only c0 and c1, and now I am going to do c2 also here. So this is going to be the same, and I'm going to get it as 1 upon s plus 2 the whole square, and that is your d by ds of f of s, and applying the limit, my c1 becomes 1 by 2 square equal to 1 by 4. Okay, I'm doing all this step because you see it more than once, it's more clear for you, and it also makes you understand it better. So, and this is pretty much everything. So here I have purposefully used the g of s to be not so complex, because doing the fractional differentiation can be very time, it can take a lot of steps, and we are not, I'm interested in showing you this, and I expect you to do a little more from these home take home questions. So that should be enough for this type of exercise question. So that should give you an idea on how to solve these questions when you do the take home exams and also your assignment questions, right? It should be fine. So now your C1 is 1 by 4, and what is your C2? Your C2 is I have to differentiate my C1 once, right? So it is d square by ds square of f of s, or which means I just have to apply my d by ds to the C1, that is d by ds of f of s. And I know what is my d by ds of f of s, that is 1 upon s plus 2 the whole square. So I am differentiating this, so this is like differentiating 1 by x square, and I'm going to get it as minus 2 by x cube. Right, so that is going to come to be d by ds of 1 upon 1 s plus 2 the whole square. I have already done my first order differentiation, so which means I am just going to plug in my d by ds of f of s as 1 by s plus 2 the whole square, because I have this computation from my previous step. And then I'm going to differentiate this 1 by s plus 2 the whole square, and I'm going to get that to be minus 2 upon s plus 2 the whole cube. So that is just how you differentiate 1 by x square. So the differential of 1 by x square is minus 2 by x cube, right? So I'm just applying that formula. Then taking the limit s tends to 0, I'm going to get that to be minus 2 by 8, and that is coming out to as minus 1 by 4. Done. So now I have my C0, C1, C2, R T, R dash T, and R double dash T. Now I can easily write my E of T as a generalized error series with my generalized error coefficient, and then I can find the ESS to be when my T takes the limit infinity, and that in this case obviously it's going to be infinity because my T comes in the numerator. So I'll write those and then I'll compute ESS, and that should be good for this generalized error coefficient. So we have done two numericals, and pretty much you get sums of this form where you have to find C0, C1 and C2, and RT, R dash T and R double dash T. And for doing both, I have shown the two numericals that should make you clear on how to proceed with such sums. And now you have these sums in your assignment questions. So please do them and then get more practice into this. So hopefully we won't see this for your exams, but if we do, you must know how to tackle these questions. All right, so I'll finish today's class with a small numerical on Hurwitz stability criterion. So this is again something, it is in the syllabus, but we are many times this just comes at the level of a very small question, like 2 to 3 mark questions, or even an MCQ question. So the question is find whether this system is stable, this polynomial system is stable or not using the Hurwitz matrix arrangement. So the polynomial is x cubed plus 6x squared plus 3x plus 2. And now what do I do is I need to write my 3 by 3 matrix, because this is a third order system with polynomial is of order 3. I'll be having a matrix which is 3 by 3, and I'm going to write the first row to be 6 1 0, right? So I'm taking that in reverse, and then the second row is 2 3 6. So you can see how the coefficients are arranged. So that is the only thing. So you get either a 3 by 3 stability matrix question or a 4 by 4 matrix question. The 4 by 4 matrix have been done in the last class. Now this is a 3 by 3 matrix, and you proceed for arranging this matrix in this manner. There is no, I can tell you many ways how this is coming in this manner, but just you can remove, because it's just a 3 by 3 matrix. The first row consists of the first two elements of the polynomial. The second row consists of the second, third, and fourth. You see the last three. That is the 2, 3, 6 are the last three polynomial coefficients, and then finally the third row has only the final constant value, that is 2, and the other things are 0. And now what are the three determinants that can be computed from this 3 by 3 matrix are shown here. So let us see whether all the determinants are positive. So the condition for Hurwitz stability is your determinant delta 1, delta 2, and delta 3 must be positive. So your delta 1 is equal to 6, and in the second case your delta 2 is 6 1 2 3, and your third case it is right. So let us write all the determinants and see whether you're getting it as positive. So for your third determinant, very difficult, I can easily tell that it's going to be a positive determinant, and because for 0 I'm not writing it because it's going to be 0, and this is coming out to be positive, I can easily tell, and I can see that all the three determinants are 0 or positive, and that makes your system stable. All right, so that's good for today. Thank you.